Welcome to the AI Show. I'm Scott Stephenson, co-founder of Deepgram. With me is Jeff Ward, aka Susan.
Hi, all.
He's a Navy pilot, acclaimed dad joke writer, and AI scientist at Deepgram. On the AI Show, we talk about all things AI. What is it? What can you do with it? How does it affect you? And where is it going? We're live and ready to take your answers, answer your questions, actually take your questions and answer them. Comment on YouTube and Twitch or tweet at Deepgram AI to join in. Today, we're asking the question, what are the top mistakes in deep learning?
Oh, man. I mean, yeah, we've got huge ones. We make them all the time.
Yeah. I think like the mistake is the rule in deep learning. You make 9 mistakes and 1 maybe good move.
Yeah, exactly. Well, how are you going to find new things if you don't make mistakes?
Oh, yeah.
Right?
I mean, it's frontier tech, right?
Exactly. And there's just so many fun pitfalls you can fall into that everybody's fallen into. I mean,
what do you think the big areas are?
Well, I think that there's really 2 major areas personally. Like there's just analyzing the problem, the basics of analyzing whatever problem you're going down, and the pitfalls around there. And then there's the model and data.
Yeah.
So if you don't analyze your problem correctly, then it really doesn't matter what you do with the model and data. You've fallen off the tracks.
Yeah.
Once you finally got a good understanding, you can get down there and fall into brand new pitfalls. I mean, have you fallen into like any analysis problems there, Scott?
There's too many to talk about, but I mean, definitely. So it's like analyze the problem, make sure your data is good. These are all good traps. Make sure your model is actually a model that would actually be able to perform the task you care about. And then in the end, you actually have to train it too, and training has its own history as well. Right,
tons.
So, but probably I can name some things that I've done, that are not good. Some of it is just when you're doing deep learning, you're doing programming, and programming is hard, right?
Yep.
Copy pasting, you're reusing old code, you're iterating as you go along, and you're kind of using like. Using the problems and errors that you're getting to kind of help you along until you finally get water through the pipes.
Oh yeah, that's a huge one. Water through the pipes.
Yeah, but usually once you first get water through the pipes and you get your first result, like everything is totally wrong anyway, right? Yeah. And so you're kind of backtracking and like, okay, where did that mistake come in?
Comes out more mud than water.
Yeah, exactly. And so
you have something.
Yeah. So it's how do you get the pieces to fit together in the model at all? How do you get even a few pieces of data into the right form to be jammed into the model? And then the model finally has to output something. And does that thing that it output make any sense at all?
Yeah.
And so biggest thing is like trying to learn an impossible task.
Oh man, I've done that.
Yeah. So don't try to do something that is impossible.
Yeah, I think I've got a fairly good rule of thumb for that one.
Yeah.
If you as a human looking at your training data can't learn the task, then I can pretty well guarantee you that no matter how good of a model builder you are, it's probably not going to be able to learn that task.
Yeah, or even if you think you can learn it, but if you ask somebody else and they're like, no, that's a totally different thing. So this is maybe something like summarizing a scientific article, and it's jammed full of information, and people would summarize it in different ways, right? And it's like, okay, maybe that's not an impossible task, but that is a very, very, very hard task.
Yeah. So the big point here is pick battles that are winnable.
Yeah.
And, make sure you're doing the steps necessary to figure out that this is a winnable battle.
Yep.
And don't lie to yourself that, the magic black box that is deep learning will be able to learn anything so long as you throw in enough data at it.
Yeah. There's so many ways that it can go wrong. You don't want the number one reason of just like, this isn't even possible to take you down. So pick something that maybe a human could do. This is a good rule of thumb. If a human could do it with maybe a second worth of thinking and come out with a very reliable answer every time, maybe that's something a machine could do.
And the second half of that is truly important. A reliable answer. What does that mean? An objective answer, something that if you had 10 humans and you asked them the same question, you would get probably 9 of them at least agreeing.
Yeah.
Because if you have 5 of them saying one thing and 5 of them saying another thing,
Yeah.
even if they're super positive, that's the right answer,
Yeah.
your machine's going to have a very hard time figuring out what side of those 5 to be on.
Yeah, ask 10 people what 5 times 5 is. Okay, maybe you can teach a machine how to do that. We know that for sure, right? But ask them what the meaning of life is, or, you know, who won the argument. You know?
Was that dress blue
Yeah.
or was that dress, you know?
Yeah.
Well, maybe that one a machine could figure out perfectly.
Maybe, yeah. But another good one, since we're talking about top mistakes in deep learning, is trying deep learning first.
Yes. Oh, yes. Yes. Figure out
like
what's
deep learning fixes everything. Well, okay, pump the brakes here a little bit.
What is the simple approach? And also, you know, you'd be surprised, just the most basic of algorithms can solve some really, really hard problems, or what we think of as hard problems. Just add it all up and find the mean, and suddenly you've got, you know, 90% of your answer in a lot of cases. So yeah, I mean, don't skip to the most complex possible huge chain answer that you can right off the bat.
You have to load up a ton of context and tools and know-how in your brain and time and the iteration cycle on deep learning is so long. You could be doing something with just regular stats or a traditional like tree-based machine learning technique or something that would go through the data and you'd have a result in like 5 minutes rather than waiting like 2 days for deep learning. You want to get on that track, like the 5 minutes, you know?
And even then, like just doing a simple least squares fit, like I've done that so many times, and that is an amazingly great, quick way to say, hey, this is a tackleable problem. And also sometimes the answer is right where you need it to be.
Yeah. You know? So don't throw away your standard stats and machine learning techniques. Go to those first. But if you think, hey, this isn't performing as well as it should, and I've turned lots of knobs, and I have a ton of data, and I have the computing power, and I have the time to go through and try and figure this out, you know, maybe try deep learning then. And it's not impossible. What about data?
Oh, man, data. You know, I'm going to tell an embarrassing story, and I'm going to I hope most people have the same embarrassing story. But, you know, I started playing around with deep learning, you know, probably just for fun, not deep learning, just machine learning in general. About 10 years ago, 15 years ago, I was playing around with little things, and then I hit the stock market like everybody does.
Yeah, first thing, ooh, machine learning, here we come.
I'm going to predict the stock market, and I started building my little model, and man, it was accurate.
Super accurate.
It was crazy accurate. It's like, I'm going to be a millionaire.
Yeah. And
what did I not do properly? Validation versus training.
Yeah. So so what you're trying to do is set up the problem. So, hey, I'm going to give you this data and you have to learn from it, but then I'm going to hold this other data out, which is true data again, but the model's never seen it. And now I'm going to show it to you and see how correct you are. Well, if you don't do that properly, then you really fool yourself.
Oh man, you can delude yourself so amazingly well. And the great thing about this particular trap, there are so many variations on this trap. It's not funny, right? You know, let's go to the, say, audiobook world, and you're trying to, I don't know, do something like speech recognition in the audiobook world, and you have 500 audiobooks, right? And 18 people reading those audiobooks.
Yep.
And you could split your data one of two ways: off of audiobook or off of people. And if I can guarantee you that if you do it off of audiobook,
well, there's 500 audiobooks.
There's 500 audiobooks, but now you suddenly look a lot better than you were because you've got the same person and you're trained versus validate.
Yeah,
right?
it learned how that person spoke in the other books, and even though it hadn't heard that exact audio before, it's heard that voice before, and it's learned a lot from that voice, and so it can do a good job on it.
Exactly. So it's not just, hey, I'm going to randomly select, and I have unfortunately learned this lesson several times in my life.
Yeah.
And
you want to know how the model performs in the wild.
Yes, exactly.
Real wild data, and this is a hard thing to just keep track of because, especially in deep learning, because it takes so long to do your experiments. It's easy to say like, well, what if I use this? Or what if I do this? What if I look over here? Well, if you train just once on one of your validation data sets,
man.
you have a big problem. You can't undo that.
No.
You can't, if you've been training your model for the last 3 months and you then spend a day training on your validation data set, you might as well throw that validation data set away, put it in your training data set, or start over on the model.
Hopefully you have a checkpoint before you did
or
that.
Or go back. Yeah,
But,
exactly. Go back into a checkpoint.
You contaminate that model and you are done.
Yeah.
And it can happen so many ways you don't even realize it. You get a new data set that you didn't realize was actually a derived data set, and it has different IDs associated with the thing it was derived from, and suddenly, wow, I'm doing really well on this, except for
training a model is not a reversible process. There's no undo button.
It's very incredibly easy to mess up your various sets of data, and so treat them wisely. But it's another great way to mess up train versus validate.
What?
Overfit your hyperparameters. Have you ever done this one?
Oh yeah, for sure. Yeah. So you're always picking like, how wide should it be? How deep should it be? How many input this do I need? How many that? And what should my learning rate be? And all these different hyperparameters. And then you try to use it on some wild data, and things aren't working.
It's like, what happened? What happened?
Yeah.
I ran 10,000 tests, each one tweaking it to be the best possible result on my validation.
Yeah.
Why isn't that matching reality?
Yeah. So you're kind of training yourself a little bit here, right?
Yeah.
It isn't that the model got adjusted so much as that you are thinking, ooh, what if I tune these knobs a little bit? And so now it does really well on your validation data set, but if you give it some real wild data, it doesn't do so well.
Yeah, it's hard to grasp at, but the first time you really truly run into it and it smacks you in the face, you definitely feel it hard. It's like that big gap between validation and reality is huge.
Yeah.
But there's still even more ways you can mess up your validation set. I mean, we could talk about this.
Well,
forever.
there's a good way to combat this, which is so you have your large training data set, and then you have a validation data set, and then you have like another validation data set, and then like another validation data set, and then you at least have these backups, so that you can test over here, test over here, test over here, get your hyperparameters where you think you need them, and then test them on these other data sets that are, maybe they're small too, like your validation data set, but at least it's giving you a little cross check, right?
Yeah. I mean, do what you can. And this also, on that note, grooming these sets as time goes on is important. Yeah. So just like, you talking about setting aside a secret or whatever you want to call these additional data sets,
test, validate, secret.
There's a lot of different ways to split these up, but if you're getting data over time, make sure that you keep on adding to these sets over time, right? Yeah. Because data changes over time, right? The English language changes over time. Yep. All it takes is, one popular new song and people shift their language a little bit. And that's just, we keep going back to the language world because that's what we think about a lot. But this is also images. Just think about how cameras have changed. Just the quality settings and all that. Your average distribution of colors are probably shifting a little bit.
Yeah, if you take a picture on an iPhone now versus 8 years ago, it's going to look vastly different.
Self-driving world. Yeah. I mean, just, if you did nothing but from the 80s, a whole bunch of video from the 80s, cars would have changed a lot. Clothes would have changed a lot. Do you think that would affect how well you can recognize everything out there, right? Yeah. All this is talking about, how you manage your data, and the disconnect between the reality of the data you're training on and the current real world production environment you're going to be on. That's the big mistake that a lot of people run into. You've been in this little locked in world, and then suddenly reality is somehow different. That's because your train, your validate probably aren't as good at representing the real world as you thought. Always fight to get it to represent.
Some other good ones are like, you have to choose your hyperparameters, which is like, how big is your network? How deep is it? How wide is it? How whatever. What learning rate are you going to use, etc. But like on the topic of learning rate, too high of a learning rate. Your gradients get huge.
Blow your weights.
It tries to learn too much too fast, and it learns nothing.
Yeah. There's so much that goes into hand tweaking all of that stuff.
Yeah.
I mean, one of the first things that you need to do is do a quick exploration, whatever mechanism you do for that grid searcher or whatever. Try to find those big hyperparameter sweet spots. But then at the same time, you've got to fight that problem of overfitting your hyperparameters, right? So it's a real challenge, and it becomes a real pitfall that you do things like wrong learning rates, and then you restart and this and that, the other, and suddenly at the end of it, you have a set of hyperparameters that seem to fit, and you've gotten into that overfit world. So minimize how often you change it.
Try to get into a good region, don't change it too much, and then rely on your data to kind of do the talking of shaping where the model should go. But you could have too low of a learning rate too, where it just like takes way too long. Like we've talked about this before, where you're kind of patience limited in deep learning because things take a while. There's a lot of parameters. It uses a lot of computational power. And if you're training models for days and it's just only getting better very slowly, like, hey, maybe your learning rate needs to be jacked up again. Again, it's part of that search. Yeah,
but that gets into sort of one that I've relearned recently, which is people pay a lot of attention to data, rightfully so, a lot of attention to model structure, rightfully so. But less attention to the optimizer that they use.
Absolutely.
And there's just an epic difference out there based off of that. The optimizer is going to, it's hard to even begin with how important that selection is. But you can forget about it.
Heuristically, it's kind of like if I know what my error is and I know kind of the errors that I've been making in the past and how far should I project where I should go? And you can think about this as a human too. It's like if you're walking around in the day and you keep hearing the same wrong thing over and over, and you're like, maybe I really need to go look into that and adjust it or something. And it's kind of weighting all of that. How much of the past should I keep for now and use in the future? How much should I throw away? And there's like a momentum side to that too. And
so sort of one way to think about it is this, going back to the classic forest problem of trying to, dense forest and how do I get to low ground? The optimizer is sort of like how fast you should be walking at any one given time.
And if it was all curvy right there, maybe you should do something else. But there are different programs there basically, or different rules that you should follow, and that's what like picking your optimizer is.
And how it adjusts that rate of walking and as you go along. But those are all big, huge, massive, things there. What about the bottom end of a model? What kind of output errors have you run into there, Scott?
What do you mean?
Well,
like a lot.
I'll give you my. I mean, I can give you my favorite one if you got one right off the top.
Not outputting good results is the biggest. Outputting all zeros when your loss function is all screwed up or whatever. But my personal favorite is outputting something that's useful in a training set, but not useful again in the real world. And forgetting the difference between training and production. I mean, when you look at code and when you look at training models and stuff like that, you're going to take this thing, you're going to wrap it in a loss function, you're going to do all these different things. And then I've honestly, I remember going and building my first models. When I actually tried to apply them to a real world problem, I realized that was completely not useful. The training set that I had been training against and the outputs I had been using there were giving me these great numbers of loss 99% accuracy.
And I was like, ooh, and I was tweaking the various settings and all that stuff. And then I disconnected the model from all that apparatus and tried to do something with it.
Feed it something real.
And suddenly it's like, I had no idea what it was actually doing. And it just had this black box of data in, black box of data out, and these metrics around it. So when you've always got to keep in your mind that the whole point is not the training set. The whole point is not the accuracy number. The whole point is not all this apparatus over there. It's when you finally get to production. What is that output supposed to look like? And how is it useful? Right? And if you can't take whatever output it's got coming out there and make it useful, then you've got to get it. You've got to address that right away. It's like the water through the pipes that you were talking about there.
Yeah.
There's water through the pipes on the training side, and also water through the pipes on the production side.
Yeah. Does it get sensible outputs in production land as well? Yeah.
Are you really able to take that 10,000 classes and do something with it, or should you have stripped it down to those 5 because that's all you cared about in production?
Yeah, so I think some real nuts and bolts ones could help too. So like not normalizing your input data.
Oh yeah, that's a
It's like, but how? What does normalizing your input data mean? It's like if you have an image, for example, and each pixel value goes from 0 to 10,000. Like, what scale should you keep it at? Should it be 0 to 10,000 or should it be some other number? And typically, machine learning algorithms are tuned to work well when you're talking about like -1 to 1 or 0 to 1 or something like that. So you should normalize your data so that 0 to 10,000 now is like 0 to 1 or something like that.
Yes. It's staggering what normalization can do for you.
Yeah.
And I mean, you just think about humans. Think about looking around your environment. The first physical step of light going into your body goes through a normalization layer, and that is, what's your eye doing right now when it stares into a light versus stares into a dark room,
It's
right?
getting smaller and bigger.
Like it shows you how important that step is that you physically do that, right? You do that with hearing too, like. It's a loud environment. What do? We put earmuffs on. We're trying to get all the sound.
Or it's loud, but it doesn't seem that loud. I mean, this is like hearing is logarithmic, essentially, right? Sure. There's tons of energy being pumped into your ear, but it's only a little bit louder.
Yeah. So normalize your data. Don't forget those initial physical filters that you can apply. Or I shouldn't say physical filters, but those initial purely simple algorithmic filters you can apply to data beforehand. I mean, again, one more on hearing.
Yeah.
When you've got 2 ears and the ability to swivel your head, and when you listen to something, when you want to really listen to something, you actually swivel your head, and that helps your hearing. That physical motion of adjusting the 2 microphones in your body to be better aligned with the source makes a big difference to understanding. So don't forget that lesson when you're in the machine learning world.
Which is a really interesting thought. We haven't discussed all that much, but essentially if you're like Amazon Alexa or Google Home or something like that, they usually have like 7 or 8 microphones on them, but humans do pretty good with just 2.
Yeah, but humans have the ability to go like this. Really easily.
They can move around. And,
so
this is kind of you have these infinite number of microphones.
Yeah, we've got a lot of great things there.
Yep, but some others are, hey, you have a deep learning model, and in there are tons of parameters, and those parameters are initialized initially to what? What do I mean by initialize? I mean, you fill up a bunch of matrices with numbers. What do you fill them with? Zeros? Is that a good answer?
Bad answer.
Very bad answer.
Very bad answer. As soon as you get to 2 layers,
do you fill them with all the
window.
same number? 1?
Nope. It can't be the same number. And even just pure randomness.
Yeah, just like linear random
is not good.
Not good.
We're not going to get into math and why, but look up some algorithms for how to fill up your parameters. When
you want it kind of round and peaked. And it's with some
based
variance
off of size, based off of number of
but
parameters.
Random still, but off a distribution.
Randomness is such an amazingly strong tool in the world. It's just crazy. And that one example shows it. You don't randomize things that literally will not learn.
Yeah.
So.
Yep. So some other cute ones are you can stitch together networks or loss functions or pieces of code that other people have written, and you use part of it, but you use it incorrectly.
Yeah.
Right? In other words, it should have a softmax that it's run through before it gets put in there, or it shouldn't. And do you strip those pieces off or not? So this is kind of an impedance mismatch, which would
This to me, this happens most going back to the training environment versus the production environment. You see this happen a lot. And this is a basic one. Luckily you fix it pretty quick just by changing that little piece of code. But in training, you may or may not need something at the end of your model that you'll strip off, for production. So keeping that in mind will help save some debugging steps. Is this really what I'm going to use it for production, or was this here just for training? I don't know, forgetting that you've got dropout set wrong or something like that.
Not turning off dropout for
dropout. So
you want it turned off for the evaluation inference probably.
You need to make sure your model's set for the right environment.
Dropout like shuts off part of the deep learning brain basically, and it's like, oh, don't you think you might want that in there? And,
So to get it in there, if you've got a bunch of parameters, you can randomly select a few of them to just ignore basically. And the important thing about this is it tries to kind of get the same level of output signal. So when you go to the production environment, you want those neurons to be there. You want those parameters to be useful. But if they were all turned on, suddenly your signal goes up by, say, 25% if you had 25% dropout on there. So you have to, you treat the evaluation side different than the train side. And some pretty important things to remember. Otherwise, you're actually, it's just not as good as it could be.
One of my favorite things to do, though, is overfitting. Which is normally a bad thing. But when you're in the water through the pipes stage where, hey, I finally got my data going, I finally got my model built, I finally have, some kind of output and I can verify that it's coming out. Now take a really small training data set, maybe just one example or maybe like 100 or maybe 8 or whatever, and train the model and make sure that you can very quickly get like 100% accurate.
You want to see that curve of learning.
Your error just drops like a rock, right? Because it's able to, the model now is just, it has so many parameters, and it's able to just focus on getting those correct. All that it's doing at that point is memorizing. But if it can't memorize those 8 things, it's probably not going to do anything else.
That helps you kind of prove that your loss function's working. It helps you prove you have some inputs and outputs that are at least in the right realm. It doesn't prove that you will have a good model structure.
You can have an awful model structure still, but at least it has some hope.
That's sort of your water through the pipes basic. All the plumbing is involved here. It is working here. So there's a ton of common big huge pitfalls. What's your, what is the biggest one like overall?
For me, it's I think the biggest one is a person hears like deep learning and like, hey, you can do anything. And it's like, okay, cool. Not anything, but there are a lot of things you can do that you couldn't do before, or it can do it better or something like that. But they think, I'm going to go to TensorFlow and then I'm going to solve my problem. Like if that's your thought process, like you got to back up a little bit and think like, we need to take baby steps here, because you're not going to just go download a model or an example or train it with a couple days of toying around and get a real production thing done. Like that's not going to happen. And even from the engineering standpoint, you're not going to do that. But from the model building standpoint, you're not going to get there basically, unless it's something super simple that you could have done with normal stats or machine learning.
I agree. The process side of the house is to me the biggest problem here. Just did you analyze the problem correctly from the start? And this is any engineering problem on the planet.
So it's like budget the appropriate amount of time, and the appropriate amount of time is at least days and probably weeks, to get a good look at that problem. And it might be months.
That might actually be the biggest pitfall in deep learning, is the assumption that it'll only be a day or two.
A day or two will have some go. That happens.
A lot.
Frequently.
That's no problem. I'll have something in a week.
Oh, weird. It's not doing what it thought it would do. But what if I just do this little trick 2 days later? Okay. And then 8 days later?
Time. It's a big time sink, that's for sure.
Absolutely. So I think that's all we have for today. Thanks for joining us on the AI show. What questions do you have about AI? Comment on YouTube or Twitch, or tweet us at Deepgram AI. We are Scott and Susan from Deepgram. We come in peace.
Certainly not robots.
And we are not robots. See you next time.
We got to finish this. Did you blink during the entire podcast?